Arumugalakshmi from Sri Jaindra Saraswati Vidyalaya Matriculation High Secondary School, Singanallur. Today we are going to discuss the problems
in Lesson 4, Electromagnetic Induction and Alternating Current.
In this video, we are going to discuss about the problems in electromagnetic induction and alternating current. First problem is, a square coil of side 30 cm with 500 turns is kept in a uniform magnetic field of 0.4 Tesla. The plane of the coil is inclined at an angle of 30 degrees to the field. Calculate the magnetic flux through the coil. So first we will write the given. The square of side A is given as 30 cm. It is in CGS unit. We have to convert it into SI unit. So 30 into 10 power minus 2 meter. So from this side we will find the area of the square, which is given by the formula A square. So 30 into 10 power minus 2 the whole square, which is equal to 9 into 10 power minus 2 meter square. This is the area of the square coil. The number of turns N is given as 500. The magnetic field B is given as 0.4 Tesla. Angle between the field and the coil theta is 90 minus 30 degrees, which is equal to 60 degree. These are the given data. Now we have to find the magnetic flux through the coil. Now we will move on to the solution. Magnetic flux is given by the formula phi is equal to NBA cos theta. The values of NBA, theta, everything we are going to substitute from the given data, which is equal to 500 into 0.4 into 9 into 10 power minus 2 into cos 60. So when you multiply all these values, you will get the flux value as 9 Weber. So the answer is the magnetic flux through the coil phi is equal to 9 Weber. Problem 2. A straight metal wire crosses a magnetic field of flux 4 milliweber in a time 0.4 second. Find the magnitude of EMF induced in the wire. So first let us start with the given data. Magnetic flux is given as 4 milliweber, which is equal to 4 into 10 power minus 3 Weber, and the time is given as 0.4 second. We are supposed to find the magnitude of the EMF induced. So the solution will start with the formula of the induced EMF, which is given by E is equal to d phi by dt, which is equal to the d phi, that is flux value is given as 4 into 10 power minus 3 divided by the time is 0.4, which is equal to 10 into 10 power minus 3 volt, which is equal to 10 millivolt. So the answer is the magnitude of induced EMF E is equal to 10 millivolt. Problem 3. The magnetic flux passing through a coil perpendicular to its plane is a function of time and is given by OB is equal to 2TQ plus 4T square plus 8T plus 8 Weber. If the resistance of the coil is 5 ohm, determine the induced current through the coil at a time t is equal to 3 seconds. So we will start the problem with the given data. The given data is magnetic flux is given by 2TQ plus 8T square plus 8T plus 8 Weber. Resistance of the coil R is equal to 5 ohm. Time is equal to 3 seconds. We are supposed to find the induced current through the coil. So the solution will start with the formula I is equal to E by R. So induced EMF E is given by d phi by dt, which is equal to d by dt of the phi value you have to substitute from the given data, which is 2TQ plus 4T square plus 8T plus 8. Now this you have to differentiate with respect to time. So 2TQ when you differentiate, it is 6T square. 4T square if you differentiate with respect to time, it is 8T, and 8T if you differentiate with respect to time, it is 8. Now here the time is given as 3 seconds. So the EMF at 3 seconds you have to substitute for t as 3. So the equation becomes 6 into 3 square plus 8 into 3 plus 8, which is equal to 54 plus 24 plus 8, which is equal to 86 volt. So the induced current through the coil I is equal to E by R, which is equal to 86 divided by 5, which is equal to 17.2 ampere. So the answer is induced current through the coil I is equal to 17.2 ampere. Now let us move on to the fourth problem. A closely wound coil of radius 0.02 meter is placed perpendicular to the magnetic field. When the magnetic field is changed from 8000 Tesla to 2000 Tesla in 6 seconds, an EMF of 44 volt is induced. Calculate the number of turns in the coil. So first let us write the given. The radius of the coil R is given as 0.02 meters. Area of the coil A is equal to pi r square. So pi value is 3.14 into r square. R value is 0.02. So the square will be 0.02 the whole square. So the area of the coil is 1.256 into 10 power minus 3 meter square. So the change in magnetic field dB is equal to 8000 minus 2000, which is equal to 6000 Tesla. Time dt is given by 6 seconds. Induced EMF E is equal to 44 volt and theta is equal to 0 degree. Now we have to find the number of turns in the coil. So we will start with the solution. Induced EMF in the coil E is given by the formula E is equal to d by dt of NBA cos theta. Here theta is equal to 0. So cos 0 is equal to 1. So 44 is equal to n into substituting the value of n, b and a. The equation becomes n into 1.256 into 10 power minus 3 into 6000 divided by 6. Here we are supposed to find the value of n. So having n on one side, taking all the numbers to the other side, we will get the equation as 44 divided by 1.256 into 6000 into 10 power minus 3 divided by 6. So the equation becomes n is equal to 44 into 6 divided by 7.536. So the number of turns is 35 turns. So the answer is the number of turns in the coil n is equal to 35 turns. Problem. A rectangular coil of area 6 cm square having 3500 turns is kept in a uniform magnetic field of 0.4 Tesla. Initially, the plane of the coil is perpendicular to the field and is then rotated through an angle of 180 degrees. If the resistance of the coil is 35 ohm, find the amount of charge flowing through the coil. So as usual, we will start with the given data. Rectangular coil of area A is given as 6 cm square. So it is in CGS unit. Whenever we do the problem in physics, we will convert all the units to SI unit. So here centimeter square is converted into meter square as 6 into 10 power minus 4 meter square. Number of turns N is given as 3500 turns. Magnetic field B is given as 0.4 Tesla. Resistance of the coil R is given as 35 ohm. Induced EMF, which is equal to change in flux per second, which is equal to phi2 minus phi1. Now we are supposed to find the amount of charge flowing through the coil. Now we will move on to the solution. EMF is given by E is equal to NBA cos 180 minus NBA cos 0. We know the value of cos 180 as minus 1 and cos 0 is 1. So substituting those values, we get the equation as minus NBA minus NBA, which is equal to minus 2 NBA. Now substitute the value of N, B and A from the given data, which is equal to minus 2 into 3500 into 0.4 into 6 into 10 power minus 4, which is nothing but minus 16,800 into 10 power minus 4, which is minus 1.68 volt. Now we can find the current flowing through the coil using the formula I is equal to E by R. E value is minus 1.68 divided by R value is 35. So the current flowing through the coil is equal to 0.048 ampere, which can also be written as I is equal to 48 into 10 power minus 3 ampere. Now we are supposed to find the amount of charge flowing through the coil, which is given by the formula Q is equal to I into T. So I value we know that it is 48 into 10 power minus 3 and T value is given as 1. So the amount of charge flowing through the coil is 48 into 10 power minus 3 coulomb. So the answer is amount of charge flowing through the coil is 48 into 10 power minus 3 coulomb. Now problem 6. An induced current of 2.5 milliampere flows through a single conductor of resistance 100 ohm. Find out the rate at which the magnetic flux is cut by the conductor. So the given data is induced current I is equal to 2.5 milliampere, resistance of the conductor R is equal to 100 ohm. We are supposed to find the rate of change of flux. So the solution is the rate of change of flux d phi by dt is equal to E. So d phi by dt is equal to E, which is equal to I into R. Now substitute the value of I and R, which is 2.5 into 10 power minus 3 into 100, which is nothing but 250 into 10 power minus 3. So d phi by dt is equal to 250 milliweber per second. So the answer is the rate of change of flux is equal to 250 milliweber per second. Seventh problem. A fan of metal blades of length 0.4 meter rotates normally to a magnetic field of 4 into 10 power minus 3 Tesla. If the induced EMF between the center and the edge of the blade is 0.02 volt, determine the rate of rotation of the blade. So given data is length of the metal blade L is equal to 0.4 meter. Magnetic field B is equal to 4 into 10 power minus 3 Tesla. So induced EMF E is equal to 0.02 volt. So the rotational area of the blade A is equal to pi r square, which is equal to 3.14 into R value is 0.4. So R square is 0.4 the whole square, which is equal to 0.5024 meter square. The induced EMF in the rotational of the coil E is equal to NBA omega sin theta. So we are supposed to find the rate of rotation of the blade. Omega we have to find. So the formula for omega is equal to E divided by BA. E value is given, B value is given and A value is given in the data. Substitute those values and we will get the equation as 0.02 divided by 4 into 10 power minus 3 into 0.5024, which is equal to 9.952 into 10 power minus 3 into 10 power 3, which is equal to 9.95 revolutions per second. So the answer is the rate of rotation of the blade omega is equal to 9.95 revolutions per second. Problem 8. A bicycle wheel with metal spokes of 1 meter long rotates in Earth's magnetic field. The plane of the wheel is perpendicular to the horizontal component of Earth's field of 4 into 10 power minus 5 Tesla. If the EMF induced across the spokes is 31.4 millivolt, calculate the rate of revolution of the wheel. So the given data is the length of the metal spokes L is equal to 1 meter. Rotational area of the spokes, which is found using the formula A is equal to pi r square. R value is given, just substitute that so that the area value will be 3.14 into 1 square, which is nothing but 3.14 meter square. The horizontal component of Earth's magnetic field is given as B is equal to 4 into 10 power minus 5 Tesla. The induced EMF E is equal to 31.4 millivolt. We are supposed to find the rate of revolution of wheel. So we know the formula omega is equal to E divided by AB. Substitute the values of E, A and B from the data given. So the equation becomes 31.4 into 10 power minus 3 divided by 3.14 into 4 into 10 power minus 5, which is equal to 250 revolutions per second. So the answer is the rate of revolution of the wheel is equal to 250 revolutions per second. Ninth problem. Determine the self-inductance of 4000 turn air core solenoid of length 2 meter and diameter 0.04 meter. So the given data is length of the air core solenoid L is equal to 2 meter, diameter D is equal to 0.04 meter, radius R is equal to diameter divided by 2, which is equal to 0.02 meter. So we can find the area of the air core solenoid, which is given by the formula A is equal to pi r square, which is equal to 3.14 into 0.02 the whole square, which is equal to 1.256 into 10 power minus 3 meter square. And the number of turns N is given by 4000 turns. The small n is found using the formula capital N divided by L. We are supposed to find the self-inductance. So the solution starts with the formula L is equal to mu naught into N divided by L the whole square into AL. So now substitute the values of mu naught, N, L, A, everything from the given data. So the equation becomes 4 into 3.141 into 10 power minus 7 into 4000 into 4000. Since it is a square, we are writing twice into 3.141 into 0.02 into 0.02 into 2 divided by 4. So the value becomes 12.62 into 10 power minus 3 Henry, which can also be written as 12.62 millihenry. So the answer is self-inductance is equal to 12.62 millihenry. Tenth problem. A coil of 200 turns carries a current of 4 ampere. If the magnetic flux through the coil is 6 into 10 power minus 5 Weber, find the magnetic energy stored in the medium surrounding the coil. So the given data is number of turns of the coil N is equal to 200, current flowing I is equal to 4 ampere, magnetic flux through the coil phi is equal to 6 into 10 power minus 5 Weber. We are supposed to find the magnetic energy stored. So the solution starts with the formula for energy stored in the coil U is equal to half L I square, where L is the self-inductance of the coil, which is given by N phi by I. Substitute this value of L in the U equation. So U is equal to half N phi divided by L into L square. So the equation becomes half N phi L. Now substitute the values of N phi and L from the given data. So the answer becomes half into 200 into 6 into 10 power minus 5 into 4, which is nothing but 2400 into 10 power minus 5 joule, which can also be written as 0.024 joules. So the answer is The energy stored in the coil U is equal to 0.024 joules. Eleventh problem. A 50 centimeter long solenoid has 400 turns per centimeter. The diameter of the solenoid is 0.04 meter. Find the magnetic flux of a turn when it carries a current of 1 ampere. So the given data is length of the solenoid L is equal to 50 centimeter, which we are supposed to convert it into SI unit, which is 50 into 10 power minus 2 meter. Number of turns per centimeter, capital N, is equal to 400. So the number of turns in 50 centimeter is given by N is equal to 400 into 50, which is equal to 20,000 into 10 power minus 2. The diameter of the solenoid D is given as 0.04 meter. Radius of the solenoid R is equal to diameter divided by 2, which is equal to 0.02 meter. So the area of the solenoid A is equal to pi r square, which is equal to 3.14 into 0.02 the whole square, which is equal to 1.256 into 10 power minus 3 meter square. And the current passing through the solenoid I is given as 1 ampere. We are supposed to find the magnetic flux. So we will start the solution with the magnetic flux formula. Phi is equal to mu n squared into Al, where mu is equal to mu naught into mu r. Mu naught value we know that it is 4 pi into 10 power minus 7. Mu r value is 1 here. So the small n is equal to capital N divided by L. So substituting these values in the flux equation, we get flux is equal to mu into N divided by L the whole squared into Al. So L get cancelled. So we get the equation as mu naught into mu r N squared A divided by L. Now substitute the values from the given data. Now we get the answer as 4 into 3.141 into 10 power minus 7 into 1 into 20,000 into 20,000 into 10 power minus 4 into 1.256 into 10 power minus 3 the whole divided by 50 into 10 power minus 2, which is nothing but 1.26 Weber. So the answer is magnetic flux is 1.26 Weber. Twelfth problem. A coil of 200 turns carries a current of 0.4 ampere. If the magnetic flux of 4 milliweber is linked with the coil, find the inductance of the coil. So the given data is number of turns N is equal to 200, current I is equal to 0.4 ampere, magnetic flux linked with the coil phi is equal to 4 milliweber, which is equal to 4 into 10 power minus 3 Weber. We are supposed to find the induction of the coil. So the self-inductance of the coil is given by the formula N phi divided by I. So substituting the values of N phi and I from the given equation, we get the answer as 200 into 4 into 10 power minus 3 divided by 0.4, which is equal to 0.8 divided by 0.4, which is nothing but 2 Henry. So L is equal to 2 Henry. So the answer is induction of the coil is equal to 2 Henry. Thirteenth problem. Two air core solenoids have the same length of 80 cm and the same cross-sectional area of 5 cm square. Find the mutual inductance between them if the number of turns in the first coil is 1200 turns and that in the second coil is 400 turns. So the given data, length of the solenoids L is equal to 80 cm, which is equal to 80 into 10 power minus 2 meter. Cross-sectional area of the solenoid A is equal to 5 cm square, which is equal to 5 into 10 power minus 4 meter square. Number of turns in the first coil N1 is equal to 1200. N2, the number of turns in the second coil is equal to 400. We are supposed to find the mutual inductance between the two coils. The mutual inductance is given by the formula mu naught into N1 divided by L into N2 divided by L into AL. Now substituting all the values from the given data, we get the answer as 4 into 3.141 into 10 power minus 7 into 1200 divided by 80 into 10 power minus 2 into 400 divided by 80 into 10 power minus 2 into 5 into 10 power minus 4 into 8 into 10 power minus 2, which is equal to 4 into 3.141 into 1200 into 400 into 5 into 80 divided by 6400 into 10 power minus 13 divided by 10 power minus 4. So which is nothing but 0.38 into 10 power minus 3 Henry, which can also be written as 0.38 millihenry. So the answer is mutual inductance between the two coils is equal to 0.38 millihenry. 14th problem. A long solenoid having 400 turns per centimeter carries a current 2 ampere. A 100-turn coil of cross-sectional area of 4 cm square is placed coaxially inside the solenoid so that the coil is in the field produced by the solenoid. Find the EMF induced in the coil if the current through the solenoid reverses its direction in 0.04 seconds. So the given data is number of turns of solenoid per centimeter is equal to 400 into 10 power minus 2. So N2 is equal to 400 into 10 power minus 2. Number of turns inside the solenoid, N1 is equal to 100. Cross-sectional area of the coil A is equal to 4 cm square, which is equal to 4 into 10 power minus 4 meter square. Current through the solenoid I is equal to 2 ampere. The time taken T is equal to 0.04 second to find the induced EMF of the coil. The solution starts with the formula of induced EMF of the coil E is equal to minus M into di by dt, where M is the mutual inductance which is given by the formula mu naught N1 N2 A2 divided by M. So substituting the values from the given data, we get the equation as 4 into 3.141 into 10 power minus 7 into 400 into 10 power minus 2 into 100 into 4 into 10 power minus 4, which is equal to 200 into 10 power minus 5 Henry. So E is equal to minus M into di by dt. Now substituting the M value here, which is equal to 200 into 10 power minus 5 into 2 divided by 0.04, which is equal to 10,000 into 10 power minus 5 volt, which is nothing but minus 0.1 volt. So the answer is induced EMF of the coil E is equal to minus 0.1 volt. Problem. A 200-turn coil of radius 2 cm is placed coaxially with a long solenoid of 3 cm radius. If the turn density of the solenoid is 90 turns per centimeter, then calculate mutual inductance of the coil. So the given data is number of turns of the solenoid N2 is equal to 200, radius of the solenoid R is equal to 2 cm, which is equal to 2 into 10 power minus 2 meter. Area of the solenoid A is equal to pi r squared, which is equal to 3.14 into 2 into 10 power minus 2 the whole square, which is equal to 1.256 into 10 power minus 3 meter square. Turn density of long solenoid per centimeter N1 divided by L is equal to 90 into 10 power 2. We are supposed to find the mutual inductance of the coil. Solution. Mutual inductance of the coil M is equal to mu naught into N1 divided by L into N2 into A2. Now substitute the values from the given data. We get the value as 4 into 3.141 into 10 power minus 7 into 90 into 10 power 2 into 200 into 1.256 into 10 power minus 3, which is equal to 2.84 into 10 power minus 3 Henry, which can also be written as M is equal to 2.84 millihenry. So the answer is Mutual inductance is equal to 2.84 millihenry. Problem 16. The solenoids S1 and S2 are wound on iron core of relative permeability 900. The area of their cross section and their length are the same and are 4 cm square and 0.04 meter respectively. If the number of turns in S1 is 200 and that in S2 is 800, calculate the mutual inductance between the coils. The current in solenoid 1 is increased from 2 ampere to 8 ampere in 0.04 second. Calculate the induced EMF in solenoid 2. So we will start the problem with the given data. Relative permeability of the iron core mu r is equal to 900. Number of turns of the solenoid S1 N1 is equal to 200. The number of turns of the solenoid S2, that is N2, is equal to 800. Area of cross section A is equal to 4 cm square, which is equal to 4 into 10 power minus 4 meter square. Length of the solenoid S1, that is L1, is equal to 0.04 meter. The current I is equal to I2 minus I1, which is equal to 8 minus 2, which is equal to 6 ampere. The time taken T is equal to 0.04 second. We are supposed to find the EMF induced in the solenoid S2 and the mutual inductance between the two coils M. So the solution starts with the expression for EMF, which is given by EMF induced in the solenoid S2 E is equal to minus M into di by dt. The mutual inductance between the coil M is given as mu naught mu r N1 N2 AL. Now substitute all these values from the given data. We get 4 into 3.141 into 10 power minus 7 into 900 into 200 into 800 into 4 into 10 power minus 4, the whole divided by 0.04. So the M value is given by 1.81 Henry. Now the EMF induced in the solenoid S2 is equal to E is equal to minus M di by dt, which is equal to minus 1.81 into 6 divided by 0.04. So the magnitude of the EMF E is equal to 271.5 volt. So the answer is the EMF is 271.5 volt and the mutual inductance is 1.81 Henry. Problem. A step-down transformer connected to a main supply of 220 volt is made to operate 11 volt 88 watt lamp. Calculate the transformation ratio and the current in the primary. So the given data is voltage in the primary coil Vp is equal to 220 volt, voltage in the secondary coil Vs is equal to 11 volt, output power is equal to 88 watt. We are supposed to find the transformation ratio K and the current in the primary, which is IP. So the solution starts with the transformation ratio equation. K is equal to Vs by Vp, which is equal to 11 by 220, which is equal to 1 divided by 20, which is 0.05. The current in the primary IP is equal to Vs by Vp into Is. So first let us find Is. After that we will substitute in this equation to get the value of IP. So Is is found from the formula output power is equal to Vs into Is. Output power is 88. So 88 is equal to 11 into Is. So Is value is equal to 88 divided by 11, which is equal to 8 ampere. Therefore IP is equal to Vs by Vp into Is. So substituting those values, 11 divided by 220 into 8, which is equal to 0.4 ampere. So the answer is the transformation ratio K is equal to 1 divided by 20, which is equal to 0.05, and the current in the primary IP is equal to 0.4 ampere. 18th problem. A 200 volt bar 120 volt step-down transformer of 90% efficiency is connected to an induction stove of resistance 40 ohm. Calculate the current drawn by the primary of the transformer. So the given data is primary voltage Vp is equal to 200 volt, secondary voltage Vs is equal to 120 volt, efficiency eta is equal to 90%, secondary resistance Rs is equal to 40 ohm. We are supposed to find Ip. So the solution starts from the current drawn by the primary of the transformer. Ip is equal to Vs into Rs into Is. So output power is equal to Vs into Is. From this equation we will find the value of Is, which is equal to Is is equal to Vs divided by Rs. So output power is equal to Vs into Vs divided by Rs. We have substituted the expression for Is here. Now what happens? Vs into Vs is Vs square divided by Rs. Now substitute the given values. So 120 into 120 divided by 40, which is equal to 360 watt. This is the output power. Now Vs into Is is equal to 360. So from this formula we can find the value of Is, which is equal to 360 divided by Vs. Vs value is 120, which is given. So Is is equal to 3 ampere. The efficiency eta is equal to output power divided by input power. So eta is equal to Vs Is divided by Vp Ip. Now substituting all those values, 90 divided by 100 is equal to 360 divided by 200 into Ip. So from this equation we can get the value of Ip, which is equal to 360 divided by 200 into 100 divided by 90, which is equal to 2 ampere. So the answer is the current through the primary is 2 ampere. Nineteenth problem. The 300 turn primary of a transformer has resistance 0.82 ohm and the resistance of its secondary at 1200 turns is 6.2 ohm. Find the voltage across the primary if the output power from the secondary at 1600 volt is 32 kilowatt. Calculate the power losses in both coils when the transformer efficiency is 80%. So the given data is efficiency is equal to 80%, which is equal to 80 divided by 100. The number of turns in primary NP is 300. The number of turns in secondary NS is equal to 1200. The resistance of the primary RP is equal to 0.82 ohm. The resistance in secondary RS is equal to 6.2 ohm. The secondary voltage Vs is equal to 1600 volt. Output power is equal to 32 kilowatt. We are supposed to find the Vp, power losses in primary and secondary coils. We start the solution with the efficiency formula. Efficiency is equal to output power divided by input power, which is equal to Vs Is divided by Vp Ip. Therefore, substituting the values, 80 divided by 100 is equal to 32 into 10 power 3 divided by input power. So, input power is got from this equation as input power is equal to 32 into 10 power 3 into 100 divided by 80, which is equal to 40,000, which can be written as input power is equal to 40 kilowatt. Now we know the transformation ratio Ns divided by Np is equal to Vs divided by Vp. So from this equation we can find the value of Vp. So Vp is equal to Vs into Np into Ns. So 1600 into 300 divided by 1200, which is equal to 400 volt. So the input power is equal to 40 kilowatt, which is equal to Vp Ip, which is equal to 40,000. So from this equation you get the value of Ip as 40,000 divided by 400, which is equal to Ip is equal to 100 ampere. So the solution starts with the equation of efficiency, which is given by output power divided by input power. So eta is equal to Vs Is divided by Vp Ip. So substituting the given data, 80 divided by 100 is equal to 32 into 10 power 3 divided by input power. So from this equation we can find the value of input power as input power is equal to 32 into 10 power 3 into 100 divided by 80, which is equal to 40,000, which can be written as 40 kilowatt. So the input power is equal to 40 kilowatt. Now we know the transformation ratio Ns divided by Np is equal to Vs divided by Vp. So from this equation we can find the value of Vp, where Vp is equal to Vs into Np divided by Ns. Now substitute the given values. 1600 into 300 divided by 1200, which is equal to 400 volt. This is the VP. Now input power is 40 kilowatt. So from this equation we can find VP into IP is equal to 40,000. So IP is equal to 40,000 divided by 400, which is equal to 100 ampere. So the output is 30 kilowatt is equal to Vs into Is. From this equation we can find the value of Is as 32,000 divided by 1600, which is equal to 20 ampere. So the output power is Vs into Is. Now, the power loss in the primary, the formula is IP square into RP. Substitute the value of IP, RP, we get the answer as 100 square into 0.82, which is equal to 8200, which can also be written as 8.2 kilowatt. Similarly, power loss in the secondary is equal to Is square into Rs, which is equal to 20 square into 6.2, which is equal to 2480, which is written as 2.48 kilowatt. So the answer is Vp is equal to 400 watt. Power loss in primary is 8.2 kilowatt and the power loss in secondary is 2.48 kilowatt. 20th problem. Calculate the instantaneous value at 60 degree, average value and RMS value of an alternating current whose peak value is 20 ampere. So we will start the problem with the given data. Peak value of current Im is equal to 20 ampere, angle theta is equal to 60 degree, which is equal to omega t. We are supposed to find the instantaneous value of current, average value of current and RMS value of current. So the solution starts with the instantaneous current formula. I is equal to Im sin omega t, which is equal to Im sin theta. Now substitute the Im and theta value from the given data. So I is equal to 20 sin 60. Sin 60 value is root 3 by 2. So 20 into root 3 by 2, which is equal to 10 root 3, which is equal to 10 into 1.732, which is equal to 17.32 ampere. So the instantaneous value of current is 17.32 ampere. The average value of current is got by the equation I average is equal to 2 into Im divided by pi, which is equal to 2 into 20 divided by 3.14. So the I average value is 12.74 ampere. Next we will find the RMS value of current, which is given by I RMS is equal to 0.707 Im. So 0.707 into Im value is 20. So 0.707 into 20, which is equal to 14.14 ampere. So the answer is instantaneous value of current I is equal to 17.32 ampere. The average value of current is 12.74 ampere and the RMS value of current is 14.14 ampere.